So today I'll promise not to count wrongly on the clock. Yesterday was off 15 minutes in my head. That's even worse than being just normally late. So today, third lecture, you could say, contract specification lifecycle management. Before we do that, I wanted to wrap up what we talked about yesterday, which I'd promised, namely resource accounting. So recall what we talked about yesterday, a foundation, a calculus, it's actually an algebra, for resource transfers. And that's generalizing actually a fundamental principle from double-entered bookkeeping. Just to repeat, we have resources in general, resources and user-defined resource types, and they can be counted. So not just numbers that we usually have in accounting. So we have an expressive algebra, and some of the parts that are interesting is by separating out the pure algebra, which has arbitrary negative amounts, and its operations from credit limits and the policy. We basically have sort of like the pretty part here. You know, we can say, oh, that always works, and then say, oh, wait a minute, we have to make sure that certain operations can only be applied if the predicate here that it's expressing a credit limit policy is satisfied. What can we do with this calculus? So think about this now as more from that perspective. So I will be not very precise at all and just give you some ideas and what you can do with this as a semantic framework for designing highly scalable resource managers. So the fundamental principle is distributed resource managers by additive decomposition. What does that mean? It means very simply, now we have a way of talking about it. The idea is that we implement a virtual distributed resource manager R by a peer-to-peer network, or by just a distributed network of resource managers. So each one of them is a resource manager, R1 through Rn. And then the definition of the internal state, the ownership states that R has is just the sum. Remember, that's the sum of transfer, the sum of ownership states of the individual resource states that we have there. So it's the sum. So in that, it's a well-defined notion. So the Ri may be distributed themselves. So you've got to think of this as saying Ri is maybe a centralized system. It's a server that's sitting in the basement, but it itself could be a decentralized or distributed system. That then again is maybe constructed in some fashion by these principles. So so the key thing is that some transfers can be locally. So imagine now we have a transfer and a resource manager validates and effects transfers. So somebody wants to have their transfer validated. So they go to Ri, to some particular one, and say, can you validate it? And then Ri says, hey, it turns out I can validate it, and it effected. So Ri then updates its own internal state and sends a message back, says it's validated and effected. Notice how much communication we've had, none amongst the different resource managers. So this was a zero communication internally about in the resource network, or resource manager network we've had. Communication was between the client submitting the transfer request and that particular resource manager. So in general, you can say, what we can do is that for any given transfer T, we might look for a useful or a good decomposition into T1 plus Tn, and then we submit T1 to R1 and Tn to Rn, and ask them to all validate these, the resource transfers. And if they all validate them, then the whole thing is validated. But if one of them doesn't validate it, then, we'd have a partial validation. So right now we don't like that. So we'd say, no, that's not happening. So we'd like to have a transactional validation of T1 through Tn. So the whole idea, of course, here is that the basic principle just says that, you know, you would have to send this out to all the resource managers. But of course, the extreme case is up here where you only send it out to one. Maybe we send it out to two, okay? So most of the TIs here will be 0. In that case, again, we're basically only sending the requests out to very few. And that's basically it. So let's see if we can do something with that. So for example, an example of a single resource manager can do it. We've seen this before. So imagine now we have R now thinking of it as a collective resource manager consisting of R1, R2 as the peers in the system. Now R1 has an internal state, let's assume of O1, which is, you know, as you can see here, you've seen this before. Bank has 60, Alice is 30, and Bob has $40. And O2, you know, we have bank 2 has $10, and Alice has 100 here. It's the same Alice, and Bob has the same, is the same agent here, has $200. And let's assume now, for simplicity, we have a 0 credit policy, so everybody has to have a non-zero balance. In that case, now let's imagine somebody Alice has authorized the transfer. So she's signed off on it, but it's not validated yet, of $80 to Bob. Now, somebody could be a contract manager, which we'll see, and we've seen actually yesterday, or Alice herself sends it off to R, but maybe she has a handle on one of the resource managers, namely R1. In that case, she sends it off to R1, and we'll find out that, well, that doesn't really work, because she has too little money in there. But usually if Alice actually knows she has to transfer money, she knows where the money is. So she might actually send it directly to R2. And R2 then will actually say, like, yes, I can validate and effect the resource transfer without any communication with R1. So there is no communication between R2 and R1. Now if we have another transfer, like, you know, Alice wanting to transfer $120 to Bob, well, it cannot be performed by any one of those resource managers. But she or somebody can decompose the transfer into, you know, T1 plus T2, $20 coming from into $20 and $100, and then submitting T1 to resource manager 1 and T2 resource manager 2, and making sure that you execute them transactionally. So you will ask both of them to execute them. So basically, can you execute it? And if you execute, both of them can execute it, then we'll say, okay, please execute them. And then we have a guarantee, and then we have a commit, and know that the update of both R1, R2 is such that the $120 collectively have been deducted. Great. Okay, so what does it mean? I won't go much further into this one. I'll use actually these operations in a little while. So nodes in the distributed resource manager need to support atomic execution of distributed transactions. We've just seen this one. If we do it like this, we'd like to have, and we need the ability to make sure that all, you know, transfer requests get executed or none at all. So a natural thing to do, it's not necessary, so there's different ways of doing this one, but a very natural approach here would be to use a simple two-phase commit protocol, which means that the resource managers, if you think about the API we've proposed so far, it said, you know, start me up, and I have a balance maybe that never changes, could be always 0 for that reason, and then I'm just receiving. I have credit policy, and then I'm receiving these transfer requests, and that's all I do. I validate and execute them, or I reject them because I can't validate them. That's all we had. So for now, it looks like we need a little bit more of an API for such a resource manager to be able to enter into distributed transactions, namely a pre-commit transfer. So it's like the apply transfer. So you're getting a transfer, and I want to apply it. And it does the same thing, but it guarantees that if validated, so it will start by validating it and say if it's not valid, then, you know, I'll reject. The pre-commit is basically one that says it fails. You know, even the pre-commit can fail, as is usually the case. If it does succeed, the pre-commit, then it says that abstractly speaking, the following is the property we want to have. Namely, if we basically execute the transfer, but such that we guarantee later on that we can apply the compensating transfer, the minus t, okay? Now remember, there's this credit policy thing. If we didn't have any credit policies, that would be always possible, okay? We wouldn't need any of this at all. But in the case where we have credit limits, maybe we have to be sure that if somebody gets a transfer in and we execute it, then we might have to undo it later on, okay? So for simple transfers, this just means that simple transfer, remember, was like transfer from A to B, okay? It's just two parties involved. It means that it's like an apply, but it deducts the resource from the sender. So do you have enough money on your account for this transfer? Yes, you do. That's wonderful. I reserve it, which means like I deduct it from your account. But I'm not going to make it available to the sender yet, okay? I'm just going to sit on it. So it deducts from the sender, but does not make it available to the receiver yet. So the receiver cannot spend it yet, okay? Then a commit transfer T means that apply previously pre-committed T, in the sense that in this case, please commit it, which means for a simple transfer, there's this amount of money in limbo, commit it now, give it to the receiver, okay? So we had these three phases. First, the money was owned by the receiver, then it went into limbo, whatever you want to call that, but it was a conceptual account, a temporary account that cannot be used by anybody else. And then that's the pre-commit, and in the commit phase it goes to either one. In the commit phase it goes to the receiver, and if we abort, it goes back to the sender. Okay. And by being in limbo, we guarantee that either one of those two is possible. Yes.
When you say that it's in limbo, is it in an actual account somewhere? Because if it's not, I feel like then maybe the sum would of the total resources would change in the system.
Yes. So you can model this in different ways, but one of them is by, as I mentioned, basically internal accounts. So yes, so you can think of it like it's a new bound account, which means it's not visible, accessible by anybody else, but the particular transaction that it's involved in. Okay, yeah, that's a good question. So the sum, the balance would still be present in the sense that we have this internal account to account for reserved amounts. So actually, you probably know these things. A pre-commit is just the same thing as when somebody reserves money on your credit card, okay? Because then they'll take the amount out of your credit limit. That's exactly what's supposed to happen. So you can't spend it. But on the other hand, they're not allowed to actually put it into their own pockets yet. If somebody reserves something, because they, in principle, could walk off with the money, but they just reserve it. So that's basically the reservation. And abort is, of course, as you could see, when we have to abort a transaction, we want to make sure that the amount is available. So if you had given it to the recipient, the recipient could have had in between some transactions and transfers to deplete the account and go down to his or her credit limit, and then there wouldn't be a possibility of transfer that amount of money back. But in this fashion, we can guarantee this. So the abstract principle or the general principle is please, dear resource manager, do whatever is required that if, the pre-commit succeeds, make sure that whatever happens in the meantime, the inverse of T will succeed, will be validated, if and when I come back to this one. Okay, so by a commit or abort. So what can you do with this? So discussion. So this is a general principle. So how can we build a virtual resource manager and build up from these kinds of component resource managers? Well, there's many dimensions. So an obvious one is by resource type. Remember, actually, we have many different resource types now that are managed by our resource managers. So a natural thing would be if you have a land registry, then the land registry manages houses and only resources of type house, okay? property. If somebody says like, could you please also manage some money? They say, not me. Okay, I don't do that. So they manage certain kinds of resource types. Now the national banking system, so you got to think of the individual banks in the national banking system as a peer in this network. This is actually what they are. Okay, so you go to them and you say, can you please manage actually, cars? No, we don't do that, but we manage United States dollars. Okay, so we do the USD resource type management. Not the only ones, but the kind of thing we do. But you could also go to the Bitcoin network. So the Bitcoin network is a resource manager, okay? So it's a single resource manager. It's just highly decentralized. And it manages one kind of account, namely Bitcoin. So it has this kind of currency type or resource type. And if somebody wants to transfer Bitcoin and dollars for a house, then we have a transfer consisting of those three. Then it's clearly the case that we have to split it up into transfers on that type, on that type, on that type, and then go to the first one and say, please do the transfer on the house, please do the transfer on the money, and please do the transfer on the Bitcoin. But let's make sure they all happen on none of them. So we can also split it up by agents. So you could say like, agents could be in arbitrary fashion, but just partition the agents you have in some fashion. So let's take all the citizens that are residents in a particular country and say that's one set of agents. And they could overlap, or even, I could be a citizen, I'm not, but some people are citizens in multiple countries, so you could be in multiple of those. But the key thing is like you could split up the set of agents. So think of that one, just not, as a partition, but, a covering of the agents you are interested in. And then you could say, I have a resource manager for every one of those subsets of the agents. In particular, you could take advantage of this. Most transfers actually, transactions will be close by. There's enormous likelihood that I will transfer money to somebody in the neighborhood and so they're in the same country, okay? So there's enormously great likelihood then that transfer can be validated by that particular resource manager without having to communicate with anybody else, okay? Nobody else needs to be involved. That's a little bit of a contrast if you think about it, how the most popular blockchain systems work. In the classic design, at the core, at level 0, at the ground level, as they sometimes say, is because if you have a transaction, a transfer in this case, of Bitcoin with your neighbor here in the US or Washington, and there's another transfer in Mongolia going on amongst neighbors, well, the whole network is very, very busy figuring out whose transfer was first. Okay. It doesn't really matter which one is first, but the whole network feels compelled to come to an agreement. It doesn't really matter who's first, but it needs to come to an agreement as to whose was first. Because then, the whole network schedules the first transfer, whatever is declared to be the first one first, and checks the credit limit, he did it, it's okay. And then there's a completely different one, it's different. And the second will also succeed. It would have succeeded in any order, okay. But you're basically establishing an order between those transfers. Notice that in this case where you have local transfers, there's no order, there's no causal dependency, so there's no dependency at all. Yeah?
In this model, how do you manage transfers between resource agents? Like, resource agent 1 could have some of my money, and the other one could have money here, and I want to transfer money between them. Because I could send a transfer here saying deduct money from my account, but that's not valid, right? Because it doesn't sum to 0.
Doesn't sum. Okay, so.
As a whole, it does
yes.
sum to 0, but not
yes.
in individual modifications.
Oh, the individual modifications. So this is actually where we had this balance account, and we model it by a bank. So if you think about it this way, what you actually do is just like in the banking system. If you transfer money from one bank to another bank, so think of a single bank as a resource manager now, all right? Then what they do is they have correspondence accounts, but they could also do it through a third bank called the central bank. And what you do is like you say like, I want to have a transfer from you to me, but I'm at a different bank, so which means at a different resource manager, and you're at the first bank. So actually what happens then is the following: is you first transfer money to an agent inside of your bank called the bank. Okay, so the bank manages accounts that include itself. Okay, then that's the first thing, you know. Then the bank transfers. So the bank has an account in the central bank. So it then has a transfer to the other bank, my bank. Okay? Same amount. And that's happening over there, up there, okay? And the one was over here. And then my bank transfers money out of its account here, locally, to my account. So these are all three transfers. They're just transfers, the sum of which has the net effect. If you add them together as vectors, that the sum effect is that you've given me money. Okay? So because the banks, in sum, you know, the bank has more money now at the central bank here, but it has lost money down here. And that's the same thing with the other bank. I think it's an interesting system, actually, this kind of hierarchical way of settlement. Because you know, you can do the following. It's like you can first, your individual transfer is not done like this in practice, and probably shouldn't be done. We've seen already it's advantageous sometimes for various reasons to collect a whole set of transfers, not only from you to everybody. So all the internal ones in your bank, we'll just execute them locally, right? But all the ones that go outside, we basically say, okay, we'll do the following. We'll take a net transfer of all of those to the bank. So that's then one transfer in that setting. It's a multi-way transfer. And then we do a single transfer of that amount, the total amount of money, really. Because the bank has gotten money and lost money, you know, has got back and forth. At the central bank, it's a single transfer up there, okay? A single amount transfer. And then there's a corresponding transfer to the recipients at the recipient bank. There's a complex transfer again happening down there. So you can compress. You have basically, instead of having, you know, n people sending transfers to m other people, you have the n people sending it to single node, the bank, by adding all the transfers. The bank is having a single simple transfer at the central bank going on. And then, so that's the n people who are transferring something out. There's a single transfer, and then there's a single m-way transfer from the recipient bank to its eventual recipients. And the reason why this works is because of arithmetic. We have you know, we have the algebraic properties. I mean, arithmetic in the sense of the algebraic properties we have here. Okay. Thanks for the question, because those properties are not presently actually utilized in systems. The properties of, you know, A plus B being able to be sometimes 0, okay? By A being an update of your UTXOs and B being an update, and then finding out, oh, they're actually canceling each other out, so I might as well not do anything at all. Summary. So I just want to say the summary here is, to me, actually, it's an algebra of transfers, and you know, it's an omega. So it's an infinite dimensional vector space. It's the reason it's not formulated with matrices, but it's just otherwise because the X and the resource types they're basically sets they're not bounded to be. They're not required to be finite. So the power of negative, I think, is important in the sense that it's wonderful to have negatives of anything. So additive inverses are important, so they give us a nice way of modeling transfers because we have negative amounts. So if you try to model this one with only positive numbers, as sometimes people try to do, you might end up in this kind of doubling, in this kind of world where you do accounting with only positive numbers, so you have to write them in one column if they're actually meant to be negative, and you have to write them in the other column if they're meant to be positive. Or you actually have to worry about things like, what if you have the order of transfers is slightly different. So if somebody has $5 and then they want to transfer $8 to you, but they're actually also in the process of getting actually $6 in, right? So if with negative, in principle, with negative balances, all these transfers will commute with each other, okay? So there's a separation of resource preservation. That's the unrestricted algebra with the negatives. And then a separate one that lets us then, specify flexible limits as to what kinds of ownership states are even, legal. So it's not so in other words, this is a flexible way then of definable credit limit strategies. It's not built in by saying, oh, everybody has to have at least zero of everything, okay? So, which is like if you build it in intrinsically by using only natural numbers or positive numbers, you get that. And the additive decomposition gives us a space of possibilities. So I haven't shown anything here, but I hope I've indicated that, oh, wow, you can come up with all kinds of designs. And the invariant I have to only worry about is actually a wonderful invariant, and it says like the sum has to be correct. But how I kind of split it up into sum ends, there's a lot of possibilities. Great. So that's okay.
So how are the resources like standardized? Or like how would you create definitions of resources? So like what's preventing someone creating like cards from non-store?
Basically nobody. So if the model really says that if you think about it, the model of resources is the co-product of over an arbitrary set. So if you think of the set as being just arbitrary strings, okay. So if somebody has, if you have a string in mind and it hasn't been used yet, you could say, oh well, that's a new resource type I've just invented, okay. So maybe I'm inventing my own currency, okay. So I have a new cryptocurrency, call it, I don't know, pardon? Oh, the OPLSS coin. It's just, as you can see, this is a real marketing stunt to call it OPLSS. It's like WWW. The only abbreviation is longer than the actual thing it abbreviates. So OPLSS coin, right? So let's do that one. And then you go off to a virtual resource manager and say, hey, please manage it for us, okay? And the resource manager is actually in principle already ready for that. It says, well, I don't know, I'll manage any kind of string as a resource type, okay? So if somebody says, here comes a transfer in, okay. Of course you have to give me some credit limits and so on, but somehow we have to get this set up. But then actually it will automatically, correctly actually already manage actually the transfers and all these things and make sure that no money is actually duplicated or lost. So in particular, if you do this one, if you're clever, don't you have to be super clever, but everybody else does it, is like you'll say, oh, the OPLSS coin, everybody has a credit limit of 0, but I have a credit limit of minus 21.4 million, right? So which means like, please, resource manager, manage it for me, and then you're rich, right? Because you got 21.4 million OPLSS coins. And at some point somebody says, I have a bicycle, and you say, I'll pay you 100 OPLSS coins for that. You can have the resource manager manage actually the account for you. So you could say, what we have here is a guarantee that resource managers, by only accepting and managing transfers, will not duplicate or lose resources. And you can invent your own. And it will make sure that people don't kind of like print Zcash coins as happened or whatever. I mean, it still has to be implemented correctly, of course, but that's the idea. So, yeah?
So, for this system, right, for this accounting system, how would you deal with like basics?
how to deal with Coinbases.
Yeah.
You have to expand on that for me.
Okay, because like you have this smart contract system, right? And you have this accounting system that adds up to 0 when you do transactions, right? And like with a Coinbase, right? If you have like a proposer, right? You get to mine and you get rewarded with a Coinbase.
Okay, so you mean mining?
Yeah.
So mining is, think about it this way, mining is the process of a special kind of transfer, okay? So the evidence of a transfer from the Coinbase, in this case, or the, being valid is that could be, the protocol you're just mentioning. It says like, oh, I'll show you the right kind of proof of computing or proof of stake or any kinds of things. Then somebody validates it, and this thing would validate and said, oh yeah, it's true. And I can see there's no credit limit maybe on that account. And the account being the Coinbase, okay? So think about it this way. Bitcoin has all kinds of, it's easy with Ethereum. Ethereum has addresses, okay? So the addresses, every address has an amount of Ether, I should say, associated with it. That's the ownership state. But think about it this way, it has one additional address, namely the Ether address, okay? And that's basically the Ether Coinbase address. And it has no credit limit. All the other ones have a credit limit of 0, and that one doesn't have one. Or maybe, we know it actually has one in the end. We've computed, but in principle it doesn't have one, okay? So you don't have to fix it. That one doesn't have one, and so mining then means that, that means at this point, this is literally what happens, if you have a mining reward, is like a transfer from that account to your account is validated and effected, okay? So in this way, you could say this extra account is keeping track of how many, coins have been, in this case, how many Ether have been issued so far. So it's the sum of the balance of all the accounts that are circulating, okay? So you could say that's a technicality, and just as we had before, by taking ownership state and just, adding whatever, the minus of the sum of that one, and then we get a transfer out of this one. That's exactly the model here, where you say that's the extra account is the Ether account, okay? And that one only engages in transfers that come from mining. Smart digital contracts. So 9:38. Now let's just talk a little bit about it. Okay. So just recall where we are now. So it's getting longer and longer, but it's actually not really that long. So what we talked about? We talked about agents. We think of them as persons, companies, robots, devices, roles of persons. You can even think of them as accounts. That's like your account at a bank is like your role at that account. So you might have multiple roles at that bank. You might have multiple accounts, okay? So those, we model them only, there's a set for now. I mean, we'll need more structure in practice, but we'll model them as sets here. Then events. There's significant real-world events that update the state of the business world, you could say, okay? So those events, we've classified into those that we just know that's a category of events that has no resource transfer effect, okay? And the other events, they have a resource transfer effect, or possibly resource transfer effect. And by resources, we meant to model physical and digital resources, and we represented them by a free vector space over resource types, okay? So the resource types are the kinds of goods, of money, and services that we add and subtract from. So the ownership states, that represents who owns what. I mean, which agent owns what, and owning in the sense of, has control over it. It could also be, dimension won't go into this, it could also be locations, could also be owners. But because the key thing is that we're modeling this by a coproduct of resource, coproduct of the resource space that's indexed by agents, okay? So it just means that it's a map, finite map, from, at any given point in time, find a map from agents to, what do they own? It's a resource. And the resource could be, a mixed compound resource consisting of all kinds of resource types. The resource transfer is just changes to the ownership. Ownership states that sum to 0. That's a way of guaranteeing that if we only update ownership states by adding such a resource transfer, we can be guaranteed the balance is never changed. So we're not duplicating or deleting anything. And a resource manager is a system that maintains these ownership states and subject to a credit limit policy. So I didn't talk about this. There's some way of specifying credit limit policies and maybe updating them, changing them, okay? So in this case, this is what I meant by the resource manager guarantees linearity of the resource management. So because it guarantees that the system here guarantees that whatever is in there will not get lost and will not get duplicated. So this is a subtle thing. I can certainly say I have a car of this kind, one car, and then I say, hey, there's two cars. Okay. Well, haven't you duplicated the car? No, I'm just talking about two cars now, right? Or I'm talking minus 14 cars, So, they can be scaled up and down, okay? So the linearity is not that we can't multiply or add resources. It's about the ownership changes maintain the balance of resources that are managed in the system. So what we'll talk about contracts extension. We already did this last time, so I'll just skip over it. And then we'll talk about escrow and CSL. So I'll get a little bit into the escrow now and then do the CSL part. So because CSL is an actual language. Okay. Until now we've only seen these semantic objects, that are denotations of contracts, but not the programs themselves or the specifications themselves. So we've seen events. We've mentioned this one. That was an example of a contract. There's residual and contract monitoring. The contract monitoring, just to go over this one again, the idea is we want to make sure that we have a system that does the following. It checks that a sequence of events is a happy path, okay? And it does this incrementally or in a streaming fashion by pulling in one event at a time and giving us an early response by saying, yeah, this still looks okay, all right? You haven't done anything wrong yet, okay? Or if you're bringing in something that says like an event that can never be complete into a sequence that will be accepted, then we'll say at this point, wait a minute, I think you don't want to do that, okay? Please do something else. That's basically all that's going on here. The alternative would be is like, if you think about it theoretically, it's like I got a contract, it denotes a set of sequences, then people just engage in events, so somebody accumulates a sequence of events, and then at the end they go to an org and say, somebody has claimed this is a happy path, they did it right. It's like, yeah, it's right, or no, that's wrong. In fact, I could have told you so after the first step already, but I didn't, because my semantics says you have to give me a complete event sequence, and then I'll tell you yes or no. So we want to get from the set of all sequences to this contract monitoring. So what can we do with this? So imagine that we have such a semantics. We can execute it in a standard fashion, or we can actually monitor it actively. So the active part consists of the following. It says many contracts, you want to make sure that they get executed to completion, so we have a happy path. Or if they don't get executed to completion, so basically there's a breach of contract in the middle. So at some point, they don't progress anymore. And by that I mean is like, somebody's trying to do something wrong, well, it gets rejected, and it's not doing anything at all. And there's always an assumption that, at some point you can ascertain that, such a sequence cannot be continued into an event sequence that is satisfactory anymore, because deadlines have expired, okay? So what do we do then? Because we had a nice contract. If for anyone, sequence is good, it's like you get something, I get something. But what if it stops in the middle? So one defensive mechanism is by saying, okay, we're interested in getting the exchanges done, the transfers done for any complete sequence. But if it gets breached in the middle so it doesn't complete, we'll roll it back. By rolling back, I mean, well, the resource transfers get rolled back, okay? So there might be all kinds of business events in there. We can't undo those. We don't want to undo those. But at least we can undo the resource transfers. The rationale is that a contract is an intent to do something good for both of us or for all of us. So the next best thing, if it doesn't succeed, is that it doesn't do any of us damage, okay? So we all retain what we owned in the beginning. This is actually where escrow comes in. Escrow is, somebody keeps the money so there is always enough of it so we can repay the original payers in case the contract doesn't complete. So as it works, we have now vocabulary to talk about this. So this is static escrow, which is actually not very efficient because it means that now we're involving and in fact this is the canonical way of a smart contract in the blockchain world, okay? So it says you want to interact with each other and transfer money to each other. What you have to do is give me all the money first, and then if I have sufficiently much money, I'll pay it out, okay? So I have my own account. I'll save that account, that money. So if somebody doesn't deliver something, it can be repaid to the original agent, and if it does, then I can transfer it to the other one. So how does it work? You could say we have a contract. It's the same contract as we did under monitoring, but now we're going to execute it under escrow, static escrow. Okay, same contract. Okay. So we haven't changed the contract, we've just changed the contract manager. So we receive a contract C0, launch a new process. So we initialize actually the contract state we're in to C0. C0 says what remains to be done. We initialize the transfer, which means the set of all transfer events that have happened, their accumulated effect, to 0, nothing. Now we receive an event and it's not validated, which means it's like a check. It's not, no resource manager has validated and effected a resource transfer yet. So it's just it's just a signed statement that A wants to transfer money to B, and it's signed by A. Okay? So that one is not sent to the bank, the resource manager, it's sent to the contract manager, this one. The contract manager receives it and says whether it's in accordance with the current contract. So is this even something needs to happen? If it doesn't need to happen or shouldn't happen or can't happen, I'll reject it. The other part I'll do is okay, if it's satisfiable, I'll update my contract to be the residual contract, and I'll update my resource transfer effect, resource transfer, to add the effect of E. So remember that was the resource transfer effect of this event. Okay. So if this says A gives $50 to B, I'll just memorize that. Okay. I'm not going to effect it, but I'll just remember that now I had an accumulated transfer effect. Now I'll just add this one to it. And if there's a business event involved, then this doesn't get updated. That's the only thing that's written down here. And I'll return accepted. So this is just a way of saying let's keep track of all the resource effects. None of them are effected. Okay. Otherwise it's rejected. So, and then, if a resource terminate request comes in, at this point, the transfer manager, at the very end, gets busy, okay? So, terminate might indicate that it's early or, out of timeout, or because it's a premature contract termination. So, premature contract termination could also be caused by timeout, which means there's no way of continuing now with the contract because it's too late. It's Thursday and you should have paid actually. The next event says that you have to pay by Wednesday. So, but in the case where it's possibly terminated, so epsilon is in the accept set, well then we'll submit T to a trusted resource manager. And remember, that sounds like, oh, which one? It could be a very big one because it could be a collection of resource managers, which I consider a virtual resource manager, okay? So this could be done by doing it transactionally. Then T submitted to a trusted research manager validation effecting. If the validation effecting succeeds, well, everything's fine, right? Because everybody had the resources they claimed to have, and it was validated. If it's not, then we'll say breach because of insufficient resources. So somebody, and we'll get an error message that says more, of course, in practice, somebody didn't have enough money or didn't have the resource they claimed to actually transfer in the contract. Okay, so in this fashion, notice that nothing happens here. We exit here in the case of breach of insufficient resources. In that case here, no resources have been transferred. Okay, so nobody has lost anything, nor gained anything. Only in the case where we reach a happy path, we are in a possibly terminated state. That's when we say, okay, now effect the resource transfer. But the disadvantage, of course, is like everybody gets their money and their things or the ownership over them at the very end. You clearly don't want to do this for a contract that lasts 30 years, like a insurance contract. But for rapid exchange, like I buy something now, and until the bicycle comes, it's okay. My money is in escrow. That's a strategy you might want to apply. Let's take a break, and then have a brief description of CSL after the break. So 10 o'clock. So you can go one step further. I won't go into it though. We could do it on the whiteboard. Maybe we'll do it in the afternoon on the whiteboard to show this one. So instead of actually locking up all the money and all the resources during a contract execution until the very end, so nobody can use it. Remember, actually, the sender has given away ownership. The receiver has not, gotten it yet. So this is locking up a lot of valuable resources. So instead of doing this one, we can ask the resource manager to actually do escrow management for us. And the advantage of this one is then all we need to make sure is that there is enough money or enough resources by the one who's actually received a resource to pay it back. Okay. Well, we'll just ask the resource manager and go, please reserve that amount of resources at any given point in time so that my contract here, at this point where it is, in this state, there's always enough money in the person's account or enough bicycles in the person's account to pay me back, okay? So intuitively you can think of this one, we'll ask the resource manager to lower the credit limit of parties according to how much they possibly could owe because they have to repay something, okay? So we're reserving, in this case, we're really reserving that amount of money. The advantage is that any agent is usually involved in lots of different contracts, okay? So all we need to do is that, the transfers can, if an agent has a lot of money in an account, there's no reason to lock up a lot of money in a contract by local escrow, you could say. We could just say, in that case, you could just transfer the money right away because there's so much money they have in their account, they will always be able to pay back what they were owing in case we have to abort. That's the story behind this one. So, but this also highlights why it's good to have, transactional. This is also exploiting the transactional interface to resource managers. CSL. Finally, let's look at a language. Okay. All right. So programming languages. So here's the L part. CSL is named. It's inspired by the name is inspired by APL. Anybody know what APL? Yeah. What does it stand for? A programming language, right? So we were actually wondering what to call this language because we thought of it as contract specification language, and at some point we got really ingenious and I thought we'll call it CSL, and we dropped the A. So this is actually rather old, you might say, but actually it's gotten renewed interest because contracts deal exactly with resource transfers, and in the old implementation we had just a centralized server someplace that managed resources. But that's really bad if you think about it because it's a trusted third party, and so blockchains are actually coming in to play that role. And you can play with it. So this is actually a commercial product now. It's open access. It's used in a number of projects, actively used in, to other companies that are doing things in areas like gold trading, or in multi-level marketing, or in a number of other areas that are quite interesting for this domain where we naturally deal with contracts. I've mentioned already some domains. So what are the design principles? I'll go into technical details later this afternoon, okay? But I think I wanted to make sure you understand basically, I wouldn't call it the desiderata or the design principles, because then you can attack them, okay? And they're basically, we're trying to combine two things and the hypothesis is that it's possible, okay? And the two things are domain adequacy and good semantic principles, okay? So, and by domain adequacy, I mean it's a domain-specific language. It's tuned to be used in a particular domain by domain specialists. And when I mean domain specialists, you should always include everybody here, okay? Because you know too much about programming, okay? But people who are working in a business domain, in a domain where they have to deal with the object, the domain itself, okay? So I can say we usually have discussions about syntax. As everybody knows, programming language people spend most time on, a little bit of time on semantics, then a little bit more time on syntax, and then much more time on lexical issues, and most time on comment formatting, okay? So we also have discussions on syntax, and sometimes I get the sense it's like the syntax sneaks in because, oh, that's from OCaml, so let's just put it in there, okay? And it's like, well, our target audience, I don't know, that's probably not OCaml programmers, okay? And so on. So that's a very important aspect of usability, by the way. I would like to, at some point, I know you have probably high-flying goals for what you want to do, but actually the study of usability of syntax, concrete syntax, was actually active until the 80s. It's been picked up a little bit in the last 5 years, I think, or so. Maybe I've seen a couple of publications in this area, but really usability studies of concrete syntax for programming languages, or in this case, domain-specific languages, I think deserves really attention. It's always dangerous to say, I like it best this way, so ergo it is best. Okay, so that's the first thing. So domain adequacy. So we're trying to capture useful patterns that we've observed that people will find is reflecting their ontology, basically the way they think about their domain. Okay. And we also actually, design principle is related to the first one, is limited expressiveness. So we want to, it's very important. It's like, don't you want it more expressive? No, you're thinking the wrong way. How can we make it less expressive, okay? So limited expressiveness for various reasons. I mean, the control and limit, the expressive language to the domain, okay? It's like, if you have a lot of furniture, that's great if it's only furniture in your basement and you find it. But if you have in your basement furniture and trucks and repair parts and I don't know, all kinds of things that are lying around, people could argue, what do you mean? I mean, the furniture is there. It's like, why are you complaining? Because it's much harder to find it, right? There's all kinds of other stuff in there. Also, you can get hurt by moving things other than furniture, right? So limited expressiveness is have domain adequacy, but not much more, if anything at all, right? So that's the idea. It's like, make sure you got what you need and that's enough. And then if you discover, I need to extend it, well, it's a domain-specific language by definition. You should face the risk of, I have to change it, okay? So the language complexity is also, should be least for the users, and we should also limit error sources. The more tools you have, the more you can shoot yourself in the foot. So let's limit those. So for example, there shouldn't be a need for computer science or programming subtleties. For example, is this a better data structure for searching? Maybe I should use hash tables here. No, they're not good enough in a. There's bad caching behavior. It's like all these things like, wait a minute, that's probably not what a business engineer should talk about. You should put that in the box that implements the CSL, but you shouldn't let the application domain specialists have to worry about that. So that's an ideal, as I said. And of course, we're also interested in, we want to increase analyzability. That's the hidden agenda in here. It's like make it as practically, maybe even theoretically, as restrictive and expressive power so we can make statements about its semantics with great precision. Well-known trade-off between analyzability and expressiveness. So the third part is like, we intended this to be really to describe protocols, like, rules that people agree on to follow, like a rule book, obligations, permissions, prohibitions. A rule book doesn't execute anything. It's just sitting there on the table. It's not walking around and taking money out of people's pockets. So it's passive, you could say. So it expresses rules to be abided by, but does not itself perform actions. So, and for that, we have, actually, we don't, but we have plans for a strategy specification language, which PT right now, the one that performs actions, that does something, that generates events, that generates actions, that's just any programming language you can use here, okay? The idea is that this is supposed to be integrated with existing ERP systems, and, and those are the ones that generate the actions. And the contracts then are the ones that monitor whether the actions are in compliance with the rules specified as a protocol. Then modularity, in the sense that you want to freely combine subcontracts into new subcontracts and respect tenants' language design principles. They basically say, like, if you have something that denotes something, you might as well be able to parameterize over it, okay? If you can declare something, then, as a variable someplace, you might also want to have a way of parameterizing over it. So it's think of it as like, design hygiene rule that usually is associated with the notion of orthogonality, okay? So you have a language that is designed such that if you have a thingamajig and it fits in this hole, you can put it there, then anything that has this kind of thing can be put in there and it makes sense. And the compositionality is actually stronger in the sense that we wanted the semantics of component combinators. So we're combining components into bigger components. We want to make sure that the combinations actually are driven by the semantics. So there's coming up with the semantics, what do these things mean, and then say, okay, now we have a real good model because we can combine actually, we have combinators, and the combinators can be described as functions on the domain, not as, functions on, taking two pieces of syntax and sticking them together, okay? So there's basically here, you can hear, this is the ideals or the principles of denotational semantics. So syntax, induction on the syntax to define the semantics of a language. So these were the design principles, and we don't know how to assert, but think about it here. This is the hidden, parts of this one, the hidden computer science agenda that we want to get away with because we think and believe there is a lot of power of what we can do with contracts, analyze them and so on, but make it such that the domain adequacy is not compromised, so it should fit together with that, okay? So here's the syntax. This is actually the original complete syntax. It's not actually much more complicated nowadays, but you can declare things and so on in Deon Digital CSL. So, the syntax says, okay, a contract, you start with it, we have a bunch of declarations, but basically a contract is either terminated successfully, we'll denote that by success, or it's a failure, which means we denote that, which means it's the empty set of sequences. We'll just write this as failure, or it's the choice between two contracts. So if you want to satisfy a contract C1 plus C2, you can do it in one of two ways. Namely, you can satisfy, the contract C1, which means a sequence of events has to satisfy C1, or it can satisfy C2. Either way is fine. Then we have par, C1 parallel with C2. This is for the concurrent Kleene interested persons. Because of the other ones, they look actually, if you look at it very hard, you will in the end see there is basically Kleene algebra. If you remove all arguments and so on, the core of it is Kleene algebra, and with that one it's concurrent Kleene algebra. So C1 parallel with C2 basic means that we are looking for an event sequence that satisfies C1 and C2, but the event sequence has to consist of events, a subsequence that satisfies C1, and another subsequence that are then interleaved together that satisfies C2. So the events that satisfy this are spread out, you could say, onto satisfying C1 and C2. So popularly speaking, both C1 and C2 have to be satisfied, okay? C1 semicolon C2, so after, C2 after C1 just means that, well, if we're looking for an event sequence that first satisfies C1, so yes, it comes into a success state, and after that we're not done, because after that we are looking for an additional event sequence that satisfies C2. Transmit, actually we've usually, and I'm preferring now to call this transfer. So transfer is, in this case, the only event we have here in general, actually, in second generation poets and also in Deon Digital. We have, these events are user definable as a whole ontology specification language, basically as type language for, type declaration language for defining, agents and resources, and in particular, events. And so in this case, there's only one event type here. But it's an interesting one because it's intended to be a transfer event, so a simple transfer. It says that A1 is of type agent, A2 is of type agent, R is of this type resource, T is of type time, and P is of type, well, it's a predicate, so we'll get to this one. But basically, it's of type agent, resource, time, and an environment to bool. Okay, so it's I call this one predicate, but as I mentioned before, it's technically speaking, it's a Boolean function. Okay, so it either returns true or false. And the dot here really means that it's a special kind of the semicolon. So it's a semicolon here, but the C here, which is important, the C here, whether something satisfies C, can depend on the actual values that the A1, A2, R, and T have had when they were matched, when we saw an event, okay? So it's depending on this one. While in the semicolon one, that's a very weak composition because it basically says, yeah, I'm not passing in on any kind of state to C2. And then that's basically it. So the rest you can think of as like, oh, okay, then we need a little bit of recursion, okay? So the recursion means that I can define parameterized in some fashion, mostly agents, resources, and times, and they're defined in definition, and then you can just instantiate, basically call one of those functions, f with some concrete values passed in as arguments. They denote a contract, okay? Namely the contract that's bound here. And letrec just means that, this is a top level thing. It just means that the definitions up here are, mutually recursive. And then inside of that scope of definitions, in that context, you then here, want to satisfy the contract C. All right, so I think I have an example, and then I'll do in the afternoon the semantics, okay, just to give you an idea. So we've seen already some intuitive ideas, but this is the 2006 version from the paper, actually. So let's look at this one. It's a letrec up here, and here's a contract, okay? Now let's look at the contract then. The contract is, well, it's a named contract, so it's one of those contract templates, we call them. So it's a sales contract, or a sale. So sale is defined up here, as you can see. So sale has...
Make it a bit bigger.
I can make it bigger, yes. Is that better?
Yes, thank you.
So sale is then instantiated with, in this case it's only strings representing agents and actually even the resources. So this is before we had the resource model I just saw before last lecture. So what is sale then? Sale is defined to be here. It's, it's this kind of, the square brackets are in the definitions, so don't get confused. It's the same thing as round parentheses. So seller, buyer, goods, payment, T1 days notice, and you can see that's the number of arguments we have. And it is defined to be, and as you can see, a dot, which means like the first thing that has to happen is a transmit event between seller, buyer, goods, and T, where T is a free variable, such that, so the seller has to be the same as this one, the buyer has to be this one, the goods has to be this one. It turns out this is actually an abbreviation of a notation, but it basically expresses that the transmit event basically has to match this with the given values here, but it can match any T. That's a free variable here. It's a binding occurrence of a variable, but the T has to satisfy a property, namely it has to be less than T1. So this basically expresses that the transmit event, this is the time it happens, the transmit event actually has to happen before T1. T1 is given here, it was the state. T1 is given here to be a valid match, to be a correct match for this transmit, okay? If you come with a transmit event, so the seller comes with a transmit event and evidence that it happened actually after T1, then the contract manager, we have no contract manager here, but then we would say, hey, that's not according to contract. If it's before T1, then yes, it is, okay. Also, if we submit, basically a transmit event by another person than the seller, it's like accidentally sent another transmit event there, it will also get rejected because it's not the seller, okay. Having said that, the contract then says that the next thing that has to happen is then that the buyer then has to send something, then we transmit to the seller the payment, specified payment, at time T prime, where T prime is also less than T1, okay? So it's kind of a little bit of a strange contract, because usually if you do this one after the other, you would imagine that you get T prime is like 2 days after T, in which case you would write, you can see the dependency then, that T prime is less than T plus 2 days, okay? And you can see that the T here is then bound by the actual concrete transmit that matches it, okay? If this happens, so if you have two events that happen in this order and they matched, then the remaining part of the contract consists of, well, either we're done, that's okay, so that's the end of the contract, or something non-conforming happens between the seller, buyer, goods, and so on. Namely that the seller says, the buyer sends something to the seller, namely a notice, and this is a business event now, sends a notice by time T. The time T is actually, it's still within D days of T1. And the message basically reads that the goods are broken, okay? So this is like a claim. And if that's done, then the seller has to do something. So remember, it's like, is it true or not what this happened? Remember always I said, there's always an assumption. Somebody has to verify things, validate things. So if something is broken, the implicit assumption is like there's evidence of it being broken, okay? So if that's the case, there's evidence, this really happened, it's broken, then the contract says that the seller has to send to the buyer half of the payment. I don't know why, but this is what the contract says, You might complain about it, but at least we know exactly what it means, okay? That's the key thing. So half the payment by at time T prime, and T prime must not be more than D days after T. And the T is the day of the notice, okay? So think of that like, was it 14 days? I couldn't remember. It was called here non-conforming notice. The notice is this one, chair broken. T prime is the days, 8 days, okay? All right, so I hope you have an intuition now, is that this is a program, and you should get an intuition already now that it denotes, what it doesn't execute anything, but it denotes a set of sequences of events that's satisfied, okay? We'll have break, and then next session starts after that, right? Oh, sorry, yeah, questions. Pardon? Yeah, well, this is, yeah, days D means D days. Pardon? So the D days, the D must be, oh, sorry, yeah. Where's the D come from? Very good question. Days D.
Doesn't it tell you that 8 refers to days? 8 days.
Yeah, but the D must be bound someplace. Or it's a constant. Good question. I'll think about it. And so I think tenant principles would say that, well, this looks like a variable, so it better be bound someplace. Because it looks like it's a binding occurrence, a bound occurrence. So it better be bound someplace. Where is it bound? Okay. And constants are also variables, but they're just bound globally. Okay. So right now I would say that the D must be a constant. I can't remember. So yeah. Yes.
So is there a notion of types here? For example, can you say that, can you send a string to denote days?
No, there is, of course, a simple type system underneath it. But yes, there's a simple type system. But I think of it more as like there's a pluggable type system. But in the paper, we have a very simple type system. Yeah.
Did you write those in this language, monitors?
In this language, we only write the contracts. Okay. The monitors, actually. A very good question, actually. We write in a different language. Right now, actually, what we did originally, this was written in, there's many of these. So the monitoring semantics saw before, there's many implementations of that one. Okay, so I think back then, we've always had a Haskell one. Okay, then there's a Java one. The current, in the commercial tooling is written in Kotlin because it runs on Corda. There's also one written in Go. So that's already another advantage in the sense, like it's the same contracts, but we can execute them on, on Hyperledger Fabric, which uses Go as its programming language. So we'll write the monitoring semantics. So the interpreter, we write that one in Go, but the input is basically always just this contract. Okay.
What's the relation between the sequencing of events and their times? Because it seems like you could write sort of.
Yes, that's a tricky issue, of course. So and if you look carefully in the paper, that's a tricky issue. But yes, so the intent is that the time is a total order, and it's consistent with the sequencing of events. So an event is basically well formed only. Sorry, an event sequence is only well formed if it's times. Every event has usually has signed a signature by an agent who submits it. Says like, I take charge of this one, I take responsibility, and the timestamp, and the timestamps have to be, non-decreasing. Sorry. Yeah. Okay. I'll see you one last time this afternoon. Thank you very much.